and welcome to the second part of this highlight lecture dedicated to Euclid. I'm Pierre Cazeneuve. I'm the Euclid French Contribution Project Manager in CNES in Toulouse, and I'm very happy to welcome you tonight. Giving talks on Euclid is always a great pleasure for me. I usually get quite easily the attention of the audience, but today is quite special. It's quite special for us in the project because when we showcase such a tremendous image, it also makes us proud, and it gives a sense on what we do on a daily basis, and that's really marvelous. And I also think that I got attention of most of the people to try to understand what's behind Euclid. So let's go behind this marvel, because we don't decide for an M-class mission just to publish nice image and take a deep dive in the universe. 90 years ago, Hubble and Lemaitre discovered that the universe was actually expanding, 90 years ago. 60 years ago, Vera Rubin discovered that we knew nothing of 80% of the matter. And finally, only 25 years ago, we realized that we knew nothing of 95% of the universe, 25 years ago only. Cosmology is one of those scientific domains where many, many unknowns remains, and working on Euclid is all about that. To give you a tour of the universe, let me introduce you to Dr. Valeria Petrolino, sorry for the Italian pronunciation, and to Professor Henk Hoekstra. Valeria is the ESA project scientist for the Euclid mission. She is a physicist, and her research focuses on cosmology, the study of the universe, dark matter, and gravity. She has joined the Euclid Consortium since the very beginning and contributed to different teams, either as a researcher or project manager. Over the years, she worked on ESA Planck and ESA Euclid mission in different institutions in Europe and in the US. She is also a member of the Supernova Foundation for Women in Astrophysics, physics. Henk Hoekstra is a professor of observational cosmology at Leiden University in the Netherlands. His research aims to shed light on dark matter and dark energy. To this end, he uses the blending of light rays on the matter, a technique he helped advance for Euclid. He is a member of the Science Coordination Group of the Euclid Consortium. His research has been supported by a number of prestigious grants, and more recently, he received an advanced grant by the European Research Council. Professor Hoekstra also engaged with the general public through lecture and collaboration with artists. And now, it's my great pleasure to leave the floor to Professor Valeria Petrolino to start the journey on Euclid.
Thank you very much. Thank you very much, everyone, for being here, for your interest in Euclid. Euclid, a mission which is designed, as we have heard, to answer some of the most fundamental questions in the study of the universe. What is the universe made of? Here, what is the universe made of? We know that luminous matter, atoms, things that form stars, and us, only account for at most 5% of the total energy content which is in the universe. The rest is the dark universe. 25% is in the form of dark matter, something which is still matter, but it doesn't emit luminous light. We don't see it directly. It feels gravity, and it's kind of the glue that makes galaxies form and stay together. And then there is 70% of something which is even more mysterious that we generically refer to as dark energy. Dark energy which drives the expansion to accelerate. The expansion of the universe goes faster and faster. However, we don't really know what's the nature of these components. What's dark energy? What's dark matter? It could be a particle, it could be new particles, it could be a new force, something that challenges even the fundamental physics of the universe, something that may change gravity and act differently at very, very large scales, differently from what Einstein had imagined in its general relativity. And the interesting thing is that in order to narrow down all these options, we need to be able to look and detect at very, very tiny effects. Because the nature of dark energy and the nature of dark matter defines how matter distributes in space. And how is that? If we look at the universe at very, very large scales, how does matter distribute in space? Does it fill up in the same way all space? Not really. What happens is that it rather forms a network, what we call a cosmic web. Quite astonishing, really. We see filaments along which clusters and galaxies group and form, and then we also see dark voids, empty spaces in between filaments. And the exact configuration, how many voids, how many clusters, how large are these voids, this depends on the nature of dark energy and of the nature of dark matter. Euclid will manage to measure this, measure the cosmic web, and how this evolves, the distribution of matter in space and in time. What we saw in the image before was just a simulation, the Euclid flagship simulation, realized on purpose for Euclid. Something that took 2 trillion dark matter particles and 2 billion of galaxies distributed in the area that would be observed by Euclid. Something really useful to assess how Euclid will perform, but then we also want to obviously look at the data, what data tell us. So we will be able, thanks to Euclid, to reconstruct the cosmic web in space and time across the past 10 billion years. That's one of the main probes of Euclid, galaxy clustering, how galaxies cluster and form. There is a second probe that Euclid will measure, and it's the distortion of light. Why is light distorted? Well, if we look at a galaxy, which is far away, and there's dark matter in between that we cannot see directly, the light that comes from this distant galaxy will not travel to us on a straight line, but it will rather be deflected around dark matter and depending on dark matter. This will deform the images of the galaxies that we see. Dark matter will act as a magnifying glass, as a lens. That's why this phenomenon is called lensing, gravitational lensing. Now, you can have very large deformations, like you see on the left, that really show even in, it's called strong lensing, so you can see even the full ring, or you can have very tiny deformations in the shape of galaxies. And these are usually not studied on a single galaxy, but rather statistically over billions of galaxies. That's why Euclid needs to observe billions of galaxies and reconstruct the shape of these galaxies in order to be able to determine what's the nature of the dark matter which is in between us and the distant sources. So we have seen the two primary probes of Euclid, galaxy clustering and lensing, gravitational lensing. This is hard, obviously, and this is also why we need to go to space. If we look at a patch of the sky from ground, this is a real image taken from ground, we're not able to measure the shapes of galaxies with the resolution that we need in order to disentangle these very tiny effects that then determine the nature of dark energy. But if we look from space, from Euclid, at the same patch, what we see is this, something which has at least 4 times the resolution that you would find from ground, and suddenly you see many, many more sources in this image. This requires, of course, to send the telescope to space and the finest optics with the instruments built in order to detect galaxies. There's 2 instruments on board of Euclid. The first is the visible imager, the VIS. It observes images of galaxies in the optical band, visible band. The second one is the NISP, the Near Infrared Spectrophotometer. It observes in the near infrared. It can act as a photometer, so detect images as well, but it's important because it also gets spectra. And spectra are important because from there we can gather distances and know how far distances galaxies are. This is essential if we want to reconstruct the evolution of the universe and therefore how fast it is expanding. And this is clearly, again, connected to the nature of dark energy. In the next slide, you'll see a photo. It's a picture of the visible instrument. This is quite an instrument. A camera of 36 detectors. Each of them 4K times 4K, so 16 megapixel, for a total of 600 megapixel. So you realize that how powerful this is. Consider that the typical phone that you have typically would have 12 megapixel in its camera. 600 megapixel there in space, and yet sending us lots and lots of data. We are currently receiving more than 100 gigabytes per day from Euclid. That's a huge amount of data. Consider that in 6 years, Euclid is meant to gather tens of petabytes of data. So this by itself is a challenge to store these data, to visualize them, to share these data, and also, of course, to process them and then allow scientists that work on this data to extract scientific information to share with the public.
5, 4, 3, 2, 1. Ignition, liftoff. Propulsion is nominal. Vehicle is pitching downrange.
And yet, this is happening. This was the launch of Euclid, 1st of July 2023. Quite a moment, quite an event for all of us and all of the thousands of people who are working on this mission. I have myself joined 16 years before that event. So consider how important it is, how special it is this moment where we are finally working with real data rather than with simulations as we have done for many, many years. Finally, we are closer to really see what dark energy and dark matter are. It took about 4 weeks for Euclid, after launch, to reach its orbit around a very special point, the second Lagrangian point, in a stable system, Sun-Earth. This is 1.5 million kilometers from Earth and rotating with Earth around the Sun. There is also a sun shield that protects the satellite from the Sun and allows it to look at the deep universe and observe galaxies. Also because this has to happen in thermal stability. Both instruments have to be cooled down. The VIS instrument at minus 120 degrees Celsius, and the NISP instrument even colder at minus 180 degrees Celsius. All to allow that resolution, that precision that we need in order to disentangle very, very tiny effects on billions of galaxies. After a few months of testing, finally, on the 14th of February 2024, this year, the nominal survey from Euclid started. And it started to map the sky, map the universe. Starting, it's what we call its wide survey. It goes quite fast. It's meant to gather at least 14,000 square degrees over a period of 6 years. And up to today, we have already observed 1,500 square degrees, about 12% of the total survey. The white survey corresponds to the lighter part that you see on top, on the bottom, and in that small island in the bottom left. In practice, this is 1/3 of the sky, but it is also all the sky that we can see beyond our galactic plane. The part in the middle is too bright, and therefore the white survey rather covers all the rest, what's beyond our galactic plane, and also the dust in our solar system. 10% of the survey is also dedicated to what's called Euclid deep fields, the 3 orange spots that you see, one in the north, 2 in the south, which were designed in order to also be very useful for astronomy. And these are patches that sum up to about 53 square degrees in the sky, in which Euclid will pass and observe several times. So while for the white survey, Euclid will see a patch and then move to the next with minimum overlap, in the Euclid deep fields, it will manage to go through that same patch several times and reach an even deeper resolution that will allow to see even fainter objects. We've seen some of the first images that have been released by Euclid to the public in the last year. These were part of a program that has been recalled before, that was the Euclid Early Release Observations. Just 24 hours of observations before the start of the nominal survey, to test that really proves that Euclid was really up to the task. And that was the case. Already scientific results were published based on these first 10 images. This is one of them from Messier 78. You can see not only how beautiful it is, but imagine that in this image there is already 300,000 sources and stars which are forming. And if you look at all the 10 images that we had released for this program, I think the most stunning thing is how diverse they look. You can see already in just 10 images, you see galaxies of different shapes, clusters, images of deep space, stars which are forming. You arrive to see, if you zoom in, even planets of the size of a few times the mass of Jupiter. So the universe is very dynamic. There's nothing static about it. There's stars are forming, galaxies are interacting, everything is moving. And you can also dive into these images by going to ESA Sky. It's a software that includes all the 10 images that had been released in the ERO program, and you can really zoom in and still see all the tiny details and sources which are included in these beautiful images. And then you are the first to see also 2 weeks of survey of data from the nominal survey. This is a sort of teaser for what will come next year in March, and then again with another data release in 2026. Just, look at this. We've seen already the fantastic video, but I still find it stunning to actually see on a big screen. This could not be possible just with a few people, right? This is a huge collaboration led by ESA, which involves people with many different expertise, different countries, companies, industry contracts, and more than 3,500 people who have worked on this project with different expertise. At this point, 2,000 of these are from the Euclid Consortium, scientists which are part of university, a network of universities and labs that would be represented here by Enke Extra, and I hand it over to him to describe the processing and more details on how the consortium works. Thank you very much.
Yes, thanks, Valeria. So let's look at these people. So folks from numbers to actually faces. And here you see sort of the group picture of a whole range of meetings. So we've been coming together for quite some years, as you can see. Really, 2011 was an important year when Euclid was selected. And we last met in Rome earlier this year. And you can see this is a large group. It's not the full consortium. So it really involves many, many people. And I like to say it takes more than a village to study dark energy. And you may wonder why. So why is this so complicated? Why do we need so many people? And that's because even though dark matter and dark energy make up 95% of the universe, the effects they impart on what we observe, right, the photons we collect with our telescopes, it's very subtle. So dark matter is invisible. There's dark matter in this room, but we don't see it. People have tried to detect it in detectors on Earth and have yet to detect it in their detectors. So it's very elusive. Dark energy is even more mysterious. And so we have this model of the universe, and as Valerio already showed, we can put the laws of physics in the computer and simulate it and create this web-like structure of dark matter. But the question is, if we launch a universe in space and it, like Euclid, it observes things, how well do we need to do? And this is, I think, very important to stress, that Euclid is in many respects also a software telescope. Right? So Valerio already explained that we want to measure the shapes of galaxies to see how space-time is distorted by the invisible dark matter. Well, to measure that directly, we would need a telescope that is very big. Because then the bigger the mirror, the sharper the image, and actually the Euclid images are not sharp enough to, out of the box, measure the shapes. So instead, we made sure we built a very stable telescope. So that adds, of course, to the cost. But in the end, we have a smaller telescope that is cheaper, but by making sure it's stable and we calibrate this very well, so for instance, how light is smeared, we can model the effects of the telescope and still get back to the resolution after the software processing that we need to measure these very, very small distortions. And so then, of course, the question is, does this line up? Right? So we see that there's a very indirect link from what we get from the telescope to what we need to measure to do dark energy. So this is why it takes so many people. It requires people doing the data processing, doing the statistics, developing the models for the new physics. So it's all very complex. And so the key bit is to make sure we get the best possible data that a telescope can deliver, and we take these pictures. We want to measure shapes, and as you know, you better not shake your camera when you're taking a picture. Right? So we want, as we scan the sky, we take a picture. Each picture is about 565 seconds, and in that period, that telescope better not move. Now, of course, everything always moves a little bit, so we have a fine guidance sensor, which does a phenomenal job now that we're in operations. But as you can see, early on, it would fail occasionally and produce these beautiful patterns of the sky, because what you see here are the tracks of bright stars as the telescope is moving around. So that clearly wasn't what we wanted, but industry very quickly figured out what the problem was and updated the software and fixed the problem. So that is allowed us to create these very beautiful images that we've seen. And there were a few more surprises as we started a mission, because Euclid was designed to really have a very, very low background of light. So that allows us to, in addition to having very sharp images, also having very deep images. And it was a bit of a shock when the early images looked like the images on the left. And basically what we figured out is that some sunlight reflected off one of the protruding thrusters that does this fine guidance sensors motion. And it was probably reflecting back from the solar panel somehow into the instrument cavity. So clearly that wasn't the plan. So somewhere a hole must have arisen for some reason. But very quickly we realized by turning the telescope a little bit so that the thruster ended up in the shadow of the sun shield, this problem went away and you get the pictures on the right. So that has some implication, because Carol Mundell already said, right, the survey is carefully planned using quite advanced algorithms, take into account all the calibrations that we need to do, keeping the orientation of the spacecraft almost within a very limited range with respect to the sun, so the thermal variations are minimal, so that everything is as stable as is humanly possible. This is the most stable telescope operational in space. But this had some ramifications because some of the freedom we used to have to carry out the survey was no longer available, but the survey has been completely replanned and we're back in operations. And that allows us to have great sensitivity to very, very faint structures. So here on the left we see a single exposure, some cosmic rays, but once we do a lot of the processing that I mentioned, we can combine these data in an image that really shows that galaxies are Milky Way-like. Right? You can see the milky structure of stars in the image there. And that's really something that is quite unique to Euclid, because in other data this tends to be buried in the noise, but because Euclid has such a nearly perfect optics and very low background, we can reveal this structure. This is something Euclid is incredibly good at. It's also important to stress that in the infrared, we take infrared data partly to get distance information, but that infrared survey is revolutionary because this is 0.5% of a single image that we take. And you see all the detail, and that's of course been emphasized also by the image that was released. We get all the detail while looking at a large part of the sky. But in the infrared, Euclid is even more revolutionary because from the ground, infrared surveys are very hard to do because the sky is very bright. To do the survey that Euclid does in 6 years, if you were to do that with the best telescopes on the ground, it would take 600 years. Right? So we're clearly completely transforming this field, and it's super exciting because we know there are very red objects out there in the universe, distant black holes, very low mass stars. They are very rare, right? If you were to look now without Euclid, you would look for a needle in a haystack, but Euclid is a machine that finds all the needles that there are to find in the haystack that we call our universe. So it's really transforming that area of research. And maybe something to emphasize, right? You can see also the star, and actually something to note, because we know when we walked around today, we saw several stands showing Euclid images. So if you want to know if a nice astronomical image is a Euclid image, look for the 5 or the 6-pointed star. Actually, over here you see it even better. Right? So if you see a star, it has 6, and that has to do with the way the telescope is made. If you see that, it's a Euclid image. So we can almost do a treasure hunt for that because there's plenty of images at this meeting that show Euclid. And so this telescope is built really well. So how the stars look is nearly perfect, right? So there's always some light smearing due to the optics, but the way, if we do the measurements around bright stars, it's essentially as good as you can theoretically do. So basically, it's limited by physics. Now, as Valerio already mentioned, we don't only make pictures, because so far I've only shown pictures. We also take what we call spectra. We spread the light out like a rainbow into spectra, and we do this, what we call slitless spectroscopy. So that has the good feature is that we get spectra for everything. The bad news is we get spectra for everything, because these spectra overlap. And so this is why we take 4 sets of exposures at slightly different angles, and again, with data processing, allows us to extract these spectra, and in the process map out this cosmic web that Valeria showed earlier on, but now traced by galaxies that emit hydrogen gas. And so, apart from the imaging thing, Euclid is also performing one of the largest spectroscopic redshift surveys ever in a redshift range that really complements from what can be done from the ground. So the more distant universe, the period where dark energy started to dominate the expansion of the universe. But also for the area I focus on, this weak gravitational lensing, we want to measure the shapes of galaxies, but we want to do more, because otherwise we just don't know where the dark matter is. So we would like to know, to make really this 3-dimensional structure, how does structure grow in the universe under the influence of dark matter, which tries to pull things together, and dark energy that tries to blow things apart. And for that we need to get distances to these 1.5 billion galaxies that we're observing. That's just too expensive to do with spectroscopy, and so therefore we use images in multiple bands. But Euclid only has 4 bands. We need about 9. So we have complemented Euclid data with a very vast collection of some of the best ground-based data that can cover such large areas of sky. Right? So essentially what we do from space is what needs to be done from space, and for cost reasons in particular, or the survey would take 30 years, we actually get lower resolution images to basically get this extra redshift information that we need. And this is a vast amount of data. This is by themselves some of the largest imaging of the whole sky at very high quality. So this is really it's not only that we want a lot of data, but we want to also ensure the quality of the data is unprecedented. And we take a lot of supporting data to calibrate things. So this is, in addition to the space data, a vast amount of data that needs to be processed. And that is done by the science ground segment. All this data has to be put together, processed, but not only processed, we have to make sure this is incredibly uniformly processed, because we're looking for very small signatures that reveal the nature of dark energy. The effects are very subtle, and we don't want to confuse new physics for a calibration error. So this is a vast amount of work. The total data set that has to be processed is order 20 terabytes. The code itself is about, when you add it all up, about 1.5 million lines of code. Requires incredible computing, and that is done distributed over 9 so-called data centers, 8 of them in Europe, 1 in the US. And this is, right, we try to estimate, this has cost at least 200 million euros. Right, this is what I said earlier. Euclid is in very regards a software telescope. The software of the telescope to actually extract those subtle signals out of the data are the price of a significant space instrument. Right? So this is really important. This allows us to get the data out of it. But that's all the organization and the instrument. Of course, that's maybe what you're interested in, but I think it's still good to emphasize the amazing science we can do with Euclid. And I want to highlight a few. So this is one of these early release observation fields, a cluster of galaxies. And from this single observation, already 3 important papers have been written. One focusing on how galaxies form as time goes on. They bang into each other, stars fly out into space, and galaxies grow, galaxies eat other galaxies. So on the left, you see a galaxy almost 100 times brighter than the Milky Way that has eaten up so many galaxies, and you see this milky glow over the image. That is all kinds of stars that have been flying out in that process. But Euclid can also see the faintest galaxies in this cluster of galaxies, and those are 4,000 times fainter than our Milky Way. So we have this incredible dynamic range, but also incredible resolution to do that. And on top of that, because of this very low background, we can actually also discover a class of galaxies that are very diffuse. You see them on the right. These are very Milky-like galaxies. We think they are really the remnants of this process of galaxy formation. They've been sort of recently discovered again, and they really can tell us if we can study in more detail about nature of dark matter. But Euclid can do so much more. The same image, we can look at the distribution of the stars in this cluster, so really you see how they've been blown out as the cluster formed. But galaxies also have what we call globular clusters. These globular clusters are also remnants of the formation of galaxies, and we see them in our Milky Way, but they're very small, they're very compact. So around other galaxies, they look like stars, like any other star in the Milky Way. But with Euclid, we can still resolve them at the distance of this cluster, and we can do something unique. We can look where these globular clusters are, and Euclid will detect about 1 million globular clusters in the nearby universe, and compare them to this starlight. And again, this allows us to reconstruct how such a large structure in the universe grew over time. And another amazing thing that Euclid can do is look in the inner regions of galaxies, and as we already heard, right, if there's a lot of mass, light gets deflected, and sometimes you can form what we call an Einstein ring. And in one of the very first images people looked at in a nearby galaxy, when they looked a bit closer, they found this amazing ring that is a unique way of measuring how much mass is there in that inner region of the galaxy. And so this is what we call strong gravitational lensing, and this allows us a unique view of the nature of dark matter on small scales, and Euclid will discover about 100,000 of those. Right now we have of order 100. And so you can imagine that is changing that field as well. So every field in extragalactic astronomy is being changed by the vast amount of data from Euclid. And just to end here, this is just the beginning, right? We've just started. You've seen the sneak preview of when we do 1%, and this is what we get from looking at a couple of images, right? It's such a rich data set, and I think the next 6 years are going to be incredibly exciting. And with that, I'll turn over back to Valeria.
Thank you, Anke. Stay with me also, because you are also part of this. Next step is next year, March 2025, there will be the Q1 data release. Q stands for quick. There's nothing quick about that, to be honest, but that's how it's called, the quick data release that will happen in March 2025. We will have a huge meeting in the Netherlands. It's called the ESLab Symposium, that will be dedicated in particular to Euclid and to the science results that will come up of this data release. This will show the first 53 square degrees of the survey, and in particular in the areas where there are the Euclid deep fields. Finally, how to engage with ESA Euclid. Here there's a few links that you may want to check out. In the top, Cosmos, ESA, Euclid, this is where you will find, for example, the data and also the scientific results, the papers which are related to the early release observations. So you can have access to those data and really also see by yourself how they look like. The website of the Euclid Consortium with all the information of how this is structured across many different universities and 17 countries. And of course, ESA Sky, where you can really dive into the images that we've seen before. Thank you very much. Also follow us on social media, on X, on ESA Euclid, and thank you very much for being here and for staying with us and listening to Euclid.